Hello, in this video, we are going to introduce our first big section test for how can we tell if a series converges or diverges. So we have this series, n equals 1 to infinity of 1 over n that we want to look at. We want to figure out if this converges or diverges. So call our definition of series converges is that the series will converge if the limit as n goes to infinity of the partial sum sequence converges. And remember that Sn means taking that sequence a sub 1 and adding the terms up until we get to the nth term. And we create a sequence this way by adding up smaller pieces of the sequence. Now, we want to know about our integral and what we know about this integral to show this series diverges. So thinking about what the integral is the area under the curve. So let's look at this function 1 over n from 1 to infinity. This sequence, as generally stated, the series is taking each of these terms and adding them up. This is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. So if I wanted to look at this sequence, it would take this point here, which is 1, this point here, which is 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Add them all up. So S sub n is equal to, as stated before, it's adding up those first n terms. However, if we look at this, since we're going between whole numbers, we've seen this idea before where we can estimate an area with a rectangle. And so the area of 1 is this rectangle from 1 to 2. And the area of 1/2 is this rectangle from 2 to 3. And this area in that third rectangle is an area of 1/3. Here's an area of 1/4, and so on. And this would continue on and on we go. Well, every single one of these rectangles is above our original curve. This is our 1/x function. And all these rectangles have area above it. So this partial sum is greater than the integral from 1 to n plus 1. Right? We'd be looking at the area from 1 to n plus 1. And adding up all of those pieces is bigger than the integral of 1 to n plus 1 of 1/x dx. The series converges if the limit of the partial sums converges. So let's take the limit of both of these. So the limit as n goes to infinity of s sub n is greater than the limit as n goes to infinity of 1 to n plus 1 integral of 1/x dx. Now this is an integral we worked just a few sections back when we were talking about improper integrals. This integral diverges. Ultimately, if we work this out, that is going to go to infinity. Working it out fully is that this is equal to the natural log of the absolute value of x. We need the limit as n goes to infinity of the natural log of x from 1 to n plus 1, which is equal to the limit as n goes to infinity of the natural log of n plus 1 minus the natural log of n of 1. The natural log of 1 is 0, but the limit as n goes to infinity of the natural log of n plus 1 is infinity. So, following this down, the limit as n goes to infinity of our partial sum sequence is bigger than infinity. Well, that means, by our definition of partial sums, the series n equals 1 to infinity of 1/n diverges because of the definition of series convergence. So, because we know the integral from 1 to infinity of 1/x dx diverges, the series does as well. This doesn't necessarily hold true for every function in series that line up, but it's true for this one. And we'll talk about the properties as to why in just a second. But what we have just shown is, thanks to the integral 1 to infinity of 1/x dx diverging, so does the series n equals 1 to infinity of 1/n. This series is actually a really special series. It is known as the harmonic series, and it diverges. So we are going to have some sections coming up where we need to know some quick series, whether they converge or diverge. Knowing geometric series are going to be very helpful there, but also knowing the harmonic series and a few other series are going to come up. So the series n equals 1 to infinity, 1/n, is known as the harmonic, and it diverges. Now, as said, not every time we're comparing a series and an integral does the series and the integral do the same thing. So not every time does the integral converge imply that the series will converge. So we can't always look at the integral, but we sometimes can. And those times we can look at the integral gives us a test known as the integral test. So suppose for some positive integer bigger than 1, we have a function that is continuous, positive, and decreasing. Let the sequence and the function be the same at the integers. So that's like our picture here, where we have our function, but the sequence just picks out these whole number inputs. So it's saying let the function and the sequence be the same at the whole number inputs. Then, if we are continuous, positive, and decreasing, the function is continuous, positive, and decreasing, then the series converges if the integral converges, and the series diverges if the integral diverges. Some big notes: we get a value at the end of the integral, or we get infinity. That value we get at the integral is not necessarily the value of the series. So when we get a number at the end of an integral, that just means that's what the integral converges to. The series has some itty bitty pieces that make it different than the integral. So the integral and the series don't converge to the same number. And then 2, if we have some higher number, k equals n, where the series converges, then it will also converge if we start at 1, since convergence is not affected by a finite number of terms. So if we can prove these facts for some number, then the integral test will work. Most times we'll use the lower bound on the series, but as long as these 3 properties, continuous, positive, decreasing, hold from some point onward, then we're good. In the next couple of videos, we'll look at examples and see this integral test in action.